Hey guys, welcome to the next video. I promised you that I will show you examples where these charts that I showed over here, like something like this in terms of where I wrote be careful, doesn't always work, and this is why it's important to understand the thought process that goes into deciding SN1, S2, E1, E2 stuff. Alright, so this is always going to be the types of questions that people who follow these charts without actually putting any thought into the question are going to get it wrong. Alright, it's very easy, they disguise it very well, right? But this is always going to trip people up, right? So please, if you're going to put these charts, it's fine. This chart above, where it's strong bases, weak bases, good nucleophils, bad nucleophils, great chart to put. I don't know if I'm not sure if I included all the stuff that you may see, but again, you could fix that by asking the T's if there's anything left out. I think I included all the important ones. But specifically this summary right here at the bottom, this is where you must be careful. Put it on your index card in terms of if you're afraid you might forget, right? You don't want to really be in a situation where you're going to get a question wrong. That could be an easy 5 points just because you forget the reaction, right? But always think the question through. Please know the thought process that goes in it. So these are going to be the questions right here. So I wrote this one out. All it says is order the following three alkyl bromides, right, with respect to increasing reactivity towards the following substitution reaction, which they've shown you in red. So this is how it was given on the test. They wrote out the stuff in red and three alkyl bromides. Now the thing is they gave it in a multiple choice format. I'm not going to give the choices out just because it's not going to, the choices are going to be all the possibilities, right? So yeah, I would say the standard six, all 6 possible answers they could have put. So what they're just asking you here is, of the following 3 structures, order them with the one that's going to be increasing in terms of reactivity, so the best for this reaction. So the first thing we need to do is figure out what reaction is showing us. They told us it's a substitution and they showed it, right? But which substitution, as in, is it SN1 or is it SN2? Well, they wrote NaN3. Remember, Na is just Na plus, cross it out, and we get N3 minus. N3 minus is a good nucleophile, but it's a bad base, okay? So we know that good nucleophiles and bad bases, generally that's going towards an SN2. Okay, so we are looking for an SN2 reaction, increasing reactivity. Okay, so out of the 3 here, so actually before you look at that, we know that SN2 prefers to have unhindered substrates, right? So methyl is always the best, then primary, then secondary, and tertiary doesn't happen, right? So looking at these 3 substrates, the easiest one to pick would have been number 3, right? It's a primary BR. So primary, this is a secondary, this is also a secondary, okay? And so primary, it's the easiest one to look at because it's better than secondary and tertiary. Sorry, we don't have a tertiary, but it's better than secondary. So we know that that's probably going to be the most reactive, right? So since that's going to be the most reactive, you know that we should just put 3 last, or the most reactive. So we have 2 spots to fill in. Now between primary and secondary, well, they're secondary, they're both secondary, so looking at the substitution alone can't help us. And the nucleophile / base is the same for both. We know it's good nucleophile, bad base. So SN2 can happen generally on a secondary when we have that situation. But how do we know which one it's going to be, right? So you see, now let's go to the chart here. Go down to the secondary, and we have a weak base, good nucleophile, SN2. Well, we already knew it was SN2. So what the heck are we going to do here, right? So you see, in this case, if you relied on the chart without essentially knowing the process behind all this stuff, this is how you're going to get stuck on the question. You're not going to be able to decide between 1 and 2 in terms of what the order is, and so you'll have a 50-50 chance at guessing the right answer. Now, in one of my previous videos, I mentioned something called beta branching. Okay, so just a quick refresher. The alpha carbon is the carbon with the leaving group. The carbons next to it are the beta carbons. Oh, it's bad. Oh boy. So the carbons next to it are the beta carbons, right, to those two carbons. So the more beta branching you have, or essentially the more things we have coming off of the beta carbons, the harder it is for SN2 to happen, all right? This is also extremely important to keep in mind because most of the time you're looking only on the carbon of the BR, but the surrounding carbons are also extremely important, right? Because think about it, our nucleophile still has to get through these two, right? So the easier time it has to get through them, the faster SN2 would happen. So looking between 1 and 2, right? 2 is going to have less things around on the beta carbons because you can see here in, let's do orange, right here, those two carbons. They both have 2 methyls off of them. The beta carbons here only have 1, so they have less beta branching. That means the less things the nucleophile has to get through, and so SN2 is going to be much faster, right? Whereas on 1, we have too much stuff around it, and so SN2 is going to be harder to happen. So 2 will be more reactive, and 1 will be the least reactive. Great? So that's a question that people would get stuck on if they're relying exclusively on the charts. Okay? Now, this isn't going to be a question, but I'm going to just show this example. So imagine you're given this, right? Br, this is primary alkyl bromide, right? So it's primary, reacting with NaN3. Remember, that's just Na plus, cross that out, that's N3 minus over DMSO. N3 minus is a good nucleophile, bad basic, we just said, right? So what's going to be the product of this reaction? Well, you can see that we have a primary leaving group, so already we can eliminate E1 and SN1. So now we have to decide between E2 and SN2. Now, remember, SN2 increases with the less stuff we have around our leaving group, right? So this is a primary, right? So you would think it's a really good, in a really good position to do SN2. Now, the only case we would get an E2 is if we had a hindered base, like terbutoxide or LDA, but we don't have that. Okay, so SN2, right? So let's draw out our product. Right, N3. So putting that answer is a really nice wrong answer on the test. It looks nice. That's not the right answer. Now, again, they wouldn't really give you this sort of question on the test formatted how I just gave it to you. It would be disguised a different way, simply because this by itself is actually no reaction. Not going to happen, right? Because, again, beta branching. When you have a beta carbon, so like here's our alpha, here's our beta. When your beta carbon is fully substituted, that's game over for SN2, right? We have 3 things coming off of our beta. It does not matter that your leaving group is on a primary carbon or that it's a good leaving group, and we have a super good nucleophile that's also a bad base. Doesn't matter. If your beta branching is full, SN2 will not happen. So we cannot get an SN2. Now I wrote no reaction. No reaction is going to be pretty much how it goes here, because you guys, there is nothing else we could have done in terms of E1, E2. Maybe you're thinking, okay, but maybe E2 can happen in this case, right? Well, we don't have even a hydrogen to use on that beta carbon to kick out the Br because that carbon has all 4 bonds. So even E2 can't happen here. And SN1 or E1 won't happen because we're not forming that primary carbocation. So, of course, they're not going to ask you this exactly how I just did. What they can ask you is arrange these in terms of, they'll give you 2 other alkyl bromides and they'll say arrange it in terms of increasing SN2 reactivity. Now, most people, because they see primary, would have put this right at the top, most reactive, when it would actually have been probably the least reactive. All right? So please watch out for something like this. They could definitely ask that. And using the chart would have gotten you this question wrong, because if you look at it, we would have immediately gone SN2 just using that chart. Not going to happen. I am going to show you one other question, and this is one of my favorite questions to show for why these charts don't always work, right? So let's see, let's draw this out here. Okay, so they're going to ask us what the major product is. Now, again, this was a multiple choice question. I'm not going to show this as a multiple choice just because we're not going to really need it. We can figure this out on our own. And again, I'm sorry for any background noise. So how do we go about this problem? Well, we have to first, again, figure out what our leaving group is. So we have OMS. Now, I didn't make a video on this stuff, but you guys actually already saw this in a lecture. OMS is a good leaving group. Yeah, so it's a good leaving group. All right. And we can see that we have a secondary leaving group. Right here, that's a secondary carbon. So we can't really eliminate SN1, SN2, U1, E2. What we now have to look at is our nucleophile or base. So this is a triple bonded with it's like an alkyl group, not an alkyl group, but just carbon chains with a negative on a carbon, and it's triple bonded. So if you didn't know it, you could use a chart for this because, like I said, this is a good chart to have. And you can see a carbon with negative and it's triple bonded to more carbons is going to be a good nucleophile, but it's also a strong base. Okay? So remember, we said that in terms of how that works. Actually, here, if we look at the chart, if we have a strong base, we get E2. You see that actually we didn't even write that if it's a strong base with a good nucleophile or a bad nucleophile. It doesn't matter. The basic character is what actually kind of predominates in terms of on a secondary. All right. So as long as you have a good base, we can go E2. So what everyone would really do is they'll see, okay, our leaving group is wedged OMS, and they'll realize that in a E2 reaction, right? In an E2 reaction, we have to take the opposite hydrogen from what our leaving group is. Our leaving group is wedged. So if I write it over here, this is going to be a wedged hydrogen. And that methyl, the hydrogen with that wedged methyl will be dashed. So everyone is going to say, oh, okay, this negative is going to grab the H here. This comes down and kicks OMS out. And they would have picked the answer that looked like this. It's going to get a double bond there, and we're still going to get this. All right. So that would have been, again, like I said, this is a multiple choice. That would have been choice A. Again, super nice wrong answer. All right. So this is what happens when you rely on a chart without actually thinking through the question. So how would I actually answer this question, right? Well, remember that in E2, or what we have in general is that this is a good base and a good nucleophile. Remember, chemistry is a cumulative subject, right? This is a base. Bases take, like we know, bases take hydrogens, protons, right? And they will prefer to take the more acidic hydrogens because an acidic hydrogen is very easy to give up. So like imagine if I have a base reacting with HCl. HCl is a very strong acid, so that H we can say is very acidic. So it's easy for the base with a here negative, grab the H and kick out the Cl. Versus something like H2O, right? Because if I do this, the H isn't really acidic on water because if you take the H, kick that out, you're going to get OH minus. OH minus is another strong base. So it'll immediately react and take the H back and form water again. It's not that acidic. So please watch out for this. Remember, these things are cumulative. These ideas will persist until you finish Orgo 2. So we took the hydrogen here. That hydrogen was on a carbon, and you can think of Oreo to help you here. That hydrogen is on a carbon. We know that carbons are not that acidic. But we have a hydrogen on an oxygen, which is more acidic, right? So the base that we have is actually going to take the hydrogen from the this OH group. We're going to get this. And we're going to have something that looks like this. Okay? So you can see, much different than anything you've seen. Very fair game, because it tests on whether you know the simple concepts of acids and bases. So acid-base stuff, please don't forget it, or just really, you gotta be prepared to understand this is a cumulative topic. Also, you may be wondering, well, why would that happen in terms of maybe, again, E2, if you're still unsure about these explanations, another one is that acid-base reactions are actually extremely fast, much faster than substitution reactions. Acid-base reactions are really fast, one of the fastest types of reactions, okay? And they'll be even faster if you have a more acidic hydrogen. So it'll take that acidic H over that H with the carbon, because that's not that acidic, all right? So we get this O with the minus charge. Now what the hell are we doing? So again, we may be now thinking, all right, you can still do an E2, right? Because I still have that dash hydrogen. And so I can just kind of come around here, grab that H, this happens, and then this happens. But that little O minus that we have, that can't really reach around like that, okay? It's going to be a little bit too hard for it to do something like this. But remember, we do have a good leaving group, right? And not only is it going to be too hard to do that, this is a case where looking at the solvent can actually help you, right? We have acetone. We know acetone is a polar aprotic solvent. Polar aprotic solvents favor SN2. Okay, so this is kind of maybe thinking, oh, maybe I'm doing an SN2, right? And we have this good leaving group right next to our nucleophile. And so what it can actually do is it's going to attack the carbon with their good leaving group and kick out the OMS. So what we're actually going to get is this weird looking structure like this. Oh, sorry, remember, we invert stereochem. And that would actually be our answer. Okay, this came from, I don't know if it was an old test, maybe an old workshop, but it was definitely from Chem 321. It was asked in the past. All right, so definitely understand the chemistry behind what you're doing. Relying on a chart is what can mess people up. Okay, so please do that. There was a multitude of answers that were given here that could look nice. We said the E2 product, right, was this. That was one of the answers that people would have picked. The other one would have been, well, they see acetone, they'll think immediately SN2, and they'll write an answer that was like this. They'll give this. That was also one of the answers, okay? So always watch out for, chemistry. This is a chemistry class, so to understand the actual fundamental ideas is important. Relying on a chart, okay, is what can screw you up. Remember, it's okay to use some shortcuts to make you maybe answer a question quicker, but to use a shortcut and not understand the chemistry behind it, that's what can really mess people up. This is going to be a huge, huge thing in Orgo 2. There's a lot of stuff that are in terms of shortcuts of how we do reactions, which are good to help you get through a question quickly. But if you don't understand the ideas behind it, it'll definitely hurt you in the long run. All right? Definitely. Never a good idea to go through to use a shortcut that you don't understand the actual fundamental concept about. So like I said, want to write this on your card, do it 100%. You never want to be in a situation where you get it wrong just simply because you forgot. You can at least have a shot at answering it if you forgot the reasoning using the chart, all right? But there will be questions where using this chart is not going to help you. A couple examples I included on my review problem set, which came from old tests and stuff like that, is they'll give you a bunch of info they'll say compounds A through E, there's like 5 of these or something, right? Or so they'll give you like 5 compounds and they'll give you a bunch of info such as like compound A, B, and C are arranged with increasing reactivity in SN2 as shown below, and they'll order them. And they'll say, if you treat B and C with another reaction, we get these. And so they're going to try to make you figure out what the reactants are using the info they give you. All right, and a lot of the times they're going to give you info that makes something super tempting, right? But using that chart is going to mess you up. So they could give you something like compound A reacts really well in terms, no, not compound A. So they'll say compound A is very slow with an SN2, right? But they could also give you another hint that it's also a primary leaving group. So now they're thinking, wait, how can a primary leaving group be really bad with SN2, right? Well, we had to think of beta branching, but your chart here doesn't tell you beta branching, okay? So remember, this isn't a chart that will 100% get you through everything. If you don't know the fundamental concepts, you're not going to be able to get 100, or maybe not even get something in terms of above a 90. All right, there are questions that weed out people who use charts without understanding a concept. Now, like I'm going to repeat myself, but like I said, put it on your card if you're worried you're going to forget it. Do not rely on these charts and not use your brains. All right, you guys are smart. Your averages have been really high. All right, shows you guys you know what you're doing. Keep doing what you're doing in terms of using your heads. Shortcuts are okay, but to use a shortcut and not understand what you're doing is not okay, especially for a classic Orgo. That can really hurt you. And like I said, if you have this habit going into Orgo 2, it's going to be very difficult for you. All right, Orgo 2 is a lot of mechanisms, a lot of reactions, much more than you guys are learning right now. Okay, much more than you guys will actually learn in Orgo 1 at all. So please understand how we're doing this. Build the good habits now in terms of actually be able to learn properly for Orgo. And you'll do really well, I promise you. Okay? So I hope this video helped you guys. The next few videos we're going to be going over, I think I'll do a couple more practice problems, but mainly we're going to go on to alcohols, right? In terms of how we can use alcohols in these reactions and turn them into good leaving groups, okay? And this is the stuff that you guys have been doing this week, I think. All right, and so we'll go over that stuff too. So I will see you guys in the next video. I hope this helped you guys. If you're still confused on something, please email me, go to the CLC. If you're watching this on YouTube, comment your question maybe so that others who have the same question can also get it answered. And I'll see you all in the next video.